colors bright, colors bold.
Vermilion, magenta, and marigold.
It's so amazing when you stop and stare. Colors, colors everywhere.
So how do I do the things that I do?
Thank you. Thank you. So Nora here has been painting, right?
Yeah.
And she has very carefully painted her hand different colors. And we've been using a couple of different colors of paint. And so paint is pigment. So mixing your pigment, that's subtractive color.
With beautiness. Da-da.
Nora wants to paint with beautiness. Yes. So if we look at Nora's rinse water, that's pretty dark. We look at the colors in the palette. Yes, it's beautiful. The colors in the palette, that's dark as well. And so you can see if you're adding blue, sort of hot pink, fluorescent yellow, and red, you're not able to see those four colors anymore. They sort of are mixing together, and you end up with this.
But you ended up with something else without using it.
Exactly.
And then you don't even play with it anymore because you're done with it.
Yes, thank you. So it's just another example of the more different shades of pigment that we mix together, the more wavelengths of color and light are.
Just did a drop on the floor.
The more wavelengths of color and light are subtracted out, coming back to the eye. So let's imagine a frog, and we'll say the frog is green. And here he is. The sun produces white light, and this includes all the colors of visible light. When the white light hits the frog, green wavelengths are reflected back to the eye, while all the other visible spectrum wavelengths are absorbed and not reflected. Here's our eye, ready to receive those green wavelengths of visible light, and they reflect to the eye, and you see green. All the other colors are absorbed. Now, the human eye has 3 cones, and they correspond to the primary colors of light, or at least that's how we see it. So we have cones that see blue light, we have cones that see green light, and we have cones that see red light. So for the human eye, our primary colors of light are blue, red, and green. We see color with this interaction of light, pigment, and cone receptors. So back to the frog and the light hitting it. Now here's our frog sitting in the sun, and he's a toasty boy. Why is he a toasty boy? Because that yellow sun produces white light, transmits white light onto the frog, and all of the wavelengths except for green are absorbed. While the green is reflected, what happens to the other wavelengths? That frog is green, but what about the other wavelengths? Conservation of energy, my dudes. Light energy that is absorbed turns into heat. This is why when you wear a white t-shirt in the sun, it feels cooler than when you wear a black t-shirt. The white shirt reflects the light energy, and the black shirt absorbs it, and it turns to heat. When we look at a table covered with different colors of plants and a fish tank with brightly colored fish, under white light we can see all of the available colors. However, this same table looks very different at night under a blue LED, with only blue wavelengths of light being transmitted to the objects, it makes everything appear in different shades of blue and black. We can see the same effect on stage in theater when we only use blue lights on the set and actors. The entire stage will appear to be in shades of blue and black. Adding white light and different kinds of filtered colored light can change the look of a stage, actors, costumes, and the overall feel of the scene. In this staging, a white light is used on the main character of Richard II, center stage, to bring focus to him. In lighting, or additive color, the more wavelengths of light that you add, the closer to white light you get. You also have 3 different primary colors: green, blue, and red. So when you mix blue light with green light and red light, you get white light. The red, green, and blue lights create shadows of the secondary colors of light: magenta, yellow, and cyan.